are from this paper, Hunting Dark Matter Lines in the Infrared Background with the James Webb Space Telescope, on which I worked together with Ryan Janisch, who is also a postdoc at Fermilab. What we did in this paper is that for the first time, we used the data from the James Webb Telescope in order to study dark matter. And to the best of my knowledge, this is also the first time that people derive constraints on dark matter by using infrared telescope. I will also show some preliminary results that will go on a follow-up paper with Ryan, where we're using more JWST data. And then, as Jorge was mentioning, I'm here because I'm collaborating with people here at the IAC on two projects. One is with the EMIR Plus, and I will tell you a little bit about it, about this idea at the very end. And also to use the Euclid Space Telescope to make projection with this great detector, and I will show you some preliminary results about that as well. Now, in the first part of my talk, I will give an introduction on dark matter. So I will tell you a little bit about what candidates we have in mind, what are the best targets that we should look at if we want to finally catch the dark matter signal, what are the main elements that enter in the computation of the dark matter signal. Then I will tell you a little bit about the experiments that I have in mind, and in particular, JWST and Euclid. And towards the end, a big chunk of this talk will actually be devoted to results and to the comparison between the bounds that we derive with what's already there in the literature. And I have a few slides about prospects, so ideas for future projects. So let's start by talking about dark matter. Now, we know that there are many evidences of the existence of dark matter in our universe at different scales, in our galaxy, in the external galaxies of the Milky Way, in cluster of galaxies, and in the cosmic web. But as of today, we really don't know what is the intimate nature of dark matter. We know it's there, but what it is. And how can we catch a signal? How can we discover what is the nature of dark matter? Well, one powerful way are the so-called indirect detection searches. Now, in indirect detection searches, the idea is that dark matter particle can annihilate or decay and produce a huge variety of astrophysical messengers. So we can study these astrophysical messengers in order to derive some of the properties of the parent dark matter particle. Now, the astrophysical messengers that you typically have in mind are photons, neutrinos, charged cosmic rays. In this talk, I will focus on photons, and I will focus on the case of decaying dark matter. But photons is a lot of things, right? So we have an entire spectrum. So what type of photons? Now, the type of photons that we expect really depends on the mass of the dark matter particles. So if we have like heavy dark matter, then we would expect gamma rays. If we have like intermediate dark matter particles, sort of like MEV or sub-GeV, we might expect even X-rays. If we have very light dark matter particles, we can use radio telescope. If we look into electron volt dark matter, which is the case of this talk, then we would expect infrared and optical photons. So that really depends on the type of dark matter that we want to study. Now, as many of you know, particle physicists have a lot of imaginary friends. Now, we like to call them dark matter candidates because it's fancier and because one of them will actually be real eventually. Now, among all the candidates that have been proposed over the years, some of the most famous are weakly interactive massive particles. Then you have like sterile neutrinos, you have primordial black holes. And today we'll focus on two of the, I think, two of the favorite dark matter candidates people are studying today, which are QCD axions and axion-like particles. Now, the QCD axions have been proposed many years ago for completely different reasons. So it has nothing to do with dark matter. People were trying to solve a different problem called the strong CP problem of QCD. Now, quantum chromodynamics is the study of the strong interaction between quarks and gluons. And particle physicists typically describe this type of interactions using Lagrangian. Now, if we look at the Lagrangian of the QCD, one of the terms is this one, where you have gluons here, then you have the strong gauge coupling, and then you have this parameter theta. Now, this Lagrangian, one can show that in principle, should violate CP, so charge parity. So basically, it shouldn't preserve the symmetry if we change the spatial coordinate or if we move from particle to antiparticle, unless this theta parameter is 0. But in principle, we do not know what is the value of this parameter. Now, one of the observational effects of this CP violation is the so-called neutron electric dipole moment. The neutron electric dipole moment is a measure of the distribution of positive and negative charges inside the neutron. And we have a non-zero value only if the center of this negative and positive charge distribution do not coincide. Now, the theory predicts a value that is order of 10 to the minus 16 plus times this parameter theta. We don't have an actual measurement. We have only an upper limit from the experiments, which tell us that this neutron electric dipole moment has to be lower than 10 to the minus 26 centimeter. That means that this parameter theta has to be much lower, like has to be something below 10 to the minus 10. So that's extremely small. So it's either 0 or it's a very, very small number. This is what we call a fine-tuning problem, because in principle, we don't have a natural explanation why this number has to be 0 or so small. Now, what happens is that over lunch, because you know that the best discussion happens when people eat. That's that's Italian people know that very well. So in 1977, Helen Quinn and Steven Weinberg were visiting Stanford University, where Roberto Peccei was a professor. And Steven Weinberg was really trying to convince that the strong CP problem was a serious problem, needs to be taken into consideration, and more people had to work on this subject. So Helen Quinn and Roberto Peccei started brainstorming, and they come up with a new theory that could explain why this theta has to be, why the strong CP problem is not a problem after all, and this theta parameter should go to 0. Now, one of the outcomes of this new theory was the production of new particles. They didn't call these particle axions. It was actually the Nobel Prize Frank Wilczek that was working with Steven Weinberg on the subject. And the reason Wilczek called them axions is from a brand of a dishwashing detergent, because the axions particle wash away and clean the strong CP problem. Now, you can see that the number of people that, the number of papers that people, and interest that people have on axions really is rising steadily. From the beginning, where there were only 16 papers, last year there were 422 papers on this subject. So particle physicists are really sort of exciting about these particles. One of the reasons is that the QCD axion can kill two birds with one stone, because it can solve the strong CP problem, but it's also a dark matter candidate. So it can explain the entire of the dark matter that we observe in our universe. And that's why people are excited about it. So the idea is that one can add these new particles, these axions, and that means in particle physics, adding new term to the Lagrangians. That's what we like to do. So the first term here, I won't give too many details, but this is just for general knowledge. The first term here depends on the gluons, then you have the axions, you have the strong gauge coupling, and you have the axion-gluon coupling. So this is the interaction between axions and gluons. This term here is the one that solves the strong CP problem. Then you have the second term. This is the term that governs the interactions between axions and photons. So you have the electromagnetic fields, these are the photons, you have the axion field, and this is the strength of these interactions. And then the third term, which I didn't even bother writing here because otherwise it's too messy, but that's the interactions with fermions. Because a lot of people are also studying the interaction, especially between axions and electrons. Now, what we care about today is the second term, so the interactions with photons. Now, it's important to state that QCD axions are a particular case of something more generic, or if you want, axion-like particles are a sort of generalization of the QCD axions. And in particular, axion-like particles do not solve the strong CP problem, but they can still be dark matter candidates and explain the entirety of the dark matter that we observe in the universe. In the case of the QCD axion, this interaction here is directly related to the mass of the axion. So that means that at the very end, when I will show you the typical dark matter parameter space, the QCD axion will live on a band. You will see a yellow band. And that's the reason is that this coupling is directly related to the mass. These correlations do not exist in the case of the axion-like particle. So that means that they can live in a much broader parameter space. But I will highlight it again later on. Just keep that in mind. So axions can interact with photons. How? Many different ways. One way is they can just decay into photons. Another way, they can be produced inside stars. So you can have that photons, they can interact with the plasma and they can produce axions. Or you can have the opposite effect. You can have that axions can convert into photons inside laboratories or astrophysical environments, provided that you have large magnetic fields. 2 and 3 depends on an effect that is called Primakov effect, and that's very typical of axions and QCD axion and axion-like particles. So today, like in my work, I focus on the axion decay, but the reason I mentioned these two is that when I will compare my results with the literature, a lot of the other results use the Primakov effect. So that's one of the most famous effects for axions. Now, the good news for the non-particle physicists in the room, which I understand it's the majority, is that you don't need to remember any of that. So the only key ideas are that axion-like particles are a generalization of this QCD axion and are great because they can be dark matter. The focus of this talk is really the interaction between axions and photons, and this interaction is characterized by this parameter GA gamma gamma, the coupling between axions and photons, and this is what we want to constrain. So the idea is that the larger this parameter, the stronger the interaction, the larger the signals. The smaller this parameter, the weaker the signal that we observe. And if you want to know more about axions, here are 3 amazing reviews. The first one, Axion Cosmology, from Pierre Sikivi, just 30 pages on the QCD axion. Then same title, different author, Axion Cosmology, from David Marsh. You can see people like this review a lot. This is a great review for axion-like particles, in particular the ultralight, which are like 10 to the minus 20 electron volt. Today we're focusing on like 1 electron volt, so it's like 20 orders of magnitude more. And then the most recent one is from Kieran Weir, Cosmology of Axion Dark Matter. This is of 2 months ago. I like this review a lot because there is a huge section on all the different detection techniques that people are implementing in order to find these axion signal. So we know what we are looking for. We're looking for dark matter, and in particular, we're looking into axions. Now, the next question is, where are we looking? What are interesting targets? So there are many. Today, we'll mention 3. Blind sky observation, so diffuse emission, dwarf galaxies, and galaxy clusters. So blind sky observation. When I say blind sky observation, I mean all the diffuse emission that fill in our beautiful universe. The pro of this, of looking into diffuse emission, is that there are really tons of archival data out there. Because when, and you can confirm, when I observationally look at a bright galaxy, they typically also take, the field next to it for sky subtraction. So, and this is great because that's where I expect my dark matter signal to background to be more favorable. I don't want to stare at a bright galaxy because it covers all my signal. I want to stare just next to it. And also, the good thing is that there is no need to apply in principle for time on the telescope. We can just use all the available archival data so that astrophysicists don't get mad at us. So that's also great. The cons of looking into diffuse emission is that depending where you look, the dark matter signal might be low. So if you look close to the galactic center, usually the signal gets higher. But if your data are far from the galactic plane, then your dark matter signal will be lower. So that's kind of a bummer. And also, you typically have less deep observation compared to the target observations. Because if your favorite astrophysicist is looking into a galaxy, obviously, they want to spend as much time as possible on the galaxy, and they will just observe these, diffuse emission for half an hour to an hour. So just for sky subtraction. I mean, in principle, so that's something that I will mention when I will also discuss the signal from dark matter. In principle, it comes from everywhere, right? So if I look like at my dark matter signal, let's say that I have my telescope and I point there, right? I can't say the signal is coming precisely from redshift 1.3. I will just observe all the signal from dark matter from the entire line of sight.
But maybe the question is, Jorge, if the dark matter signal comes from the Milky Way halo, was your question?
Partly, yes, but it will also be extragalactic. So you have both. Yeah, in principle, you have both. Yeah. If you look closer to the galactic center, obviously it will be mostly galactic. That really depends. Like the further away you look, the more it will be like extragalactic, and the closer you look to the galactic plane, the more will be like your galactic plane. Yeah.
From the Milky Way. But if it doesn't, then I mean, if the signal comes from the circumgalactic medium or
it will come. Yeah, it will come also.
You
that,
don't care about that. That's why I got a little bit lost when you mentioned the galactic center. But
okay.
Fine. So
yeah.
sorry for the
No. That's if you have a question, interrupt me anytime. It's more fun. Okay, so dwarf galaxies. We like dwarf galaxy because they are dark matter dominated. That's great. So you typically have also here a favorable signal to background ratio, which is what you want when you look for dark matter. And they're also relatively close to us. So that's also a pro. What I like about dwarf galaxy is also that you have a lot of complementary searches in other wavelengths. With gamma rays, you have like data from Fermi and Magic. For optical, you have Muse. So you can see the same object in different wavelengths, and you can learn more. The cons is that the signal might be lower compared to diffuse emission if you look in the right direction. And you also might have a lot of uncertainties, especially if you look into ultra faint galaxies, dwarf galaxies. And then you have galaxy clusters. Galaxy clusters, a lot of galaxies there, and that means a strong dark matter signal. Also, galaxy clusters are expected to host a large population of subhalos, and that boosts your signal. But the problem is that they are far away from us, typically, certainly further than the dwarf galaxy that we consider. And also the contribution of the substructures, it's sort of uncertain. So that adds a level of uncertainty to your analysis. Now, the reason it's important to consider different targets is that if you expect the dark matter signal, you would expect to see it in all these targets. So let's say that you look at the dwarf galaxy and you see a signal that kind of look like dark matter. Then you should see that signal also in the galactic center, then you should see that signal also in galaxy clusters. But when you look at in diffuse emission, but when you look at your astrophysical background, the expected astrophysical background will be very different if you look at different targets or in different wavelengths, for instance. So that's an effective way to sort of try to disentangle your dark matter contribution from your astrophysical background, because that's a sort of our enemy, right? As particle physicists, we really want to get rid of this background, and that's overwhelming. So how can we do it in an effective way? And one way is to look at different targets. So now, how do we compute our dark matter signal? What are the main elements? Now, this is the typical flux, differential flux of spectrum that I expect from dark matter. This depends on the decay emission rate. So the decay emission rate or the decay lifetime of dark matter, if you prefer. It depends on the mass of the dark matter particle. It depends on the emission spectrum. So here we're considering photons, dark matter decaying to photons. But in principle, if I consider, for instance, a weakly interactive massive particle as candidate, these are usually heavier, GV, TV scale, and they might decay into BB bar quarks. And this can give you gamma rays. Or you can consider dark matter decaying to electrons and positrons. So these are all different channels, and they will all enter in this red element here. And then there is the D factor, which takes into account the line of sight. And I will tell you a bit about this in, I think, 2 slides. So let's see about one by one, this element. If I look at the decay emission rate, the decay emission rate is the inverse of the decay lifetime. It depends on the axion photon coupling. So when I showed you before the Lagrangian, I said you have the interaction between photon and axions that are governed by this parameter. That's the one that we care about. And this parameter is directly related to the emission rate, or vice versa. The emission rate goes with like g squared and with the cube of the axion. Then you have the D factor. That's what I was saying before replying to the question. When I look in a certain direction in the sky, I can't really say the dark matter is coming from that specific redshift. I just receive all the, the signal coming from the entire line of sight. So what I have to do is that I have my density profile, and I have to integrate over the entire line of sight to have my cumulative emission. There are techniques to separate the signal, but in this case, you just see all of it. And so one question is like, what's the dark matter profile? Now, when you do extragalactic dark matter, typically people are happy with the NFW profile. The closer you get to the galactic center, the closer people get uncomfortable with this assumption. And in particular, if you look here, you have the dark matter profile as a function of the distance from the galactic center. You can see that NFW is the blue curve. Then you have a more cast profile, which is in red. And then you have, this was supposed to be dark green. It looks like gray, but it's dark green. Say again. Yes, yeah, absolutely. That's a Burkert profile. So you can see that the closer you go to the galactic center, the more you have like 5 orders of magnitude different, which is kind of huge. Well, if you go a few kiloparsec or like 10 kiloparsec far from the galactic center, they converge to the same. So that depends on the target that you're looking at, but that can make a big difference. Now, in the results that I will show you, they mostly come from far from the galactic center, so that really doesn't matter, but it's good to keep that in mind. Then you have the emission spectrum. So in our case, again, we're considering dark matter decaying directly into photons, so we might be tempted to just consider a simple delta. But we should always take into account that our actions are moving, and so are we. So there is a Doppler effect that needs to be taken into consideration, and we do. And then also, your detector has a finite resolution. So you really need to take into account the instrumental response, and that depends on the telescope that you have in mind. So what telescope do we have in mind? Now we'll tell you very briefly a little bit about the information on JWST and Euclid that we need to move on. So JWST has 4 instruments on board. NIRCam, NIRI, NIRIS, and NIRSpec. Now, 2 of these are imaging telescope. I'm sure you can do great science with it, but not the kind that I care about. So for me, what's important is really to work with spectrograph. Because at the end of the day, I want to compare my dark matter, like the spectrum from dark matter that I expect from dark matter, to the spectrum that is observed from a certain target. So I love spectrograph. And there are 2 spectrographs that are on board of the JWST. One is the NIRSpec, near infrared spectrograph, and that covers the wavelength range between 0.6 and 5 micron. And then you have MIRI, mid-infrared instrument, that goes to larger wavelength, 1.9 to 27.9 micron. That's good because if I have an instrument that looks at different wavelength, to me, that means that I can explore different masses of dark matter. Now, the results that I will show you today are all related to NIRSpec. But with Ryan, we're also looking now into MIRI for the same reason of exploring more masses. I'm not part of a collaboration, but I like to show the pictures because I think it's important to give credit to the people that make it possible to work with this data. So this is a nice picture of the JWST collaboration. And I think I like this because you can see how big the detector is compared to us humans. So it's quite big. I will tell you more about JWST when I will show you the observations, because in the case of JWST, we have data already public. Now we'll tell you a little bit about Euclid. So Euclid is a huge collaboration, 2,600 members, that's a lot. 300 laboratories, 17 different countries. It's mostly Europeans, 14 European countries, and then there is also US, Canada, and Japan that are involved. This is like a picture of the launch in Florida last year. And now Euclid is orbiting together with JWST and Gaia. It's like 3 friends all orbiting together. So when we look at the mission objectives of Euclid, it's really in the name. Because Euclid of Alexandria was this Greek mathematician that was studying was considered the founder of geometry. And we know that the density of matter and energy in our universe really determine the geometry that we observe. So the mission Euclid is really the purpose of building this three-dimensional map by measuring the redshift and shape of galaxies up to redshift 2. And what is the Euclid timeline? So Euclid is up there just a year, less than a year. And the mission lifetime will be at least 6 years and a half. And now we start to have data that we can use for research. There will be 3 main data release, each one with like a quick data release before, just to sharpen our analysis tool before the main data release. This is an imaging and a spectroscopic survey in the visible and near infrared. So this is the wavelength range. It will cover a survey area of 15,000 degrees. That means 1/3 of the sky, which is great because usually when you do diameter searches, the more sky you cover, the better. And each year we'll cover different regions. So year 1 is in green, 2 in red, then you have in blue year 3, 4 in orange, purple is 5, and the last year is in yellow. There are 2 main detectors, visible imaging instrument and the near infrared spectrometer. That's the one I care about because again, I want a spectrum. And if we look at the spectroscopy that I can do with Euclid, this is the wavelength range, the sensitivity, and the spectral resolution. Now notice the spectral resolution is not great. It's like 250. Compare with JWST, the NIRSpec, they have I think 3 high resolution gratings that are like 2700, so it's like 1 order of magnitude bigger than that. There are like 3 medium gratings that are more like 1000. And then there is a prism that is similar, it's like 100. So like the resolution is not great, but we can still use it for diameter searches. And EMIR is even more, because like 3,000-4,000, I think. So what are the observations? So in the first study, the one that I showed you in the first slide, we consider just one observation of one target. Now, this apparently is a very famous galaxy for astrophysicists. As a particle physicist, I never heard of it before. So this is a high-redshift galaxy in the constellation of Ursa Major. And apparently until 2022 was the most distant known galaxy. And this year it was discovered to contain the most distant black hole known in the universe. So how many things particle physicists discover? We look at data from astrophysics. What it's important for what I do is to know where it is, because that changes the amount of dark matter that I expect, the location. The D factor, it's a quantity, you know, like I showed you before, it's how much dark matter there is there. 10 to the 2022 is a lot, typically, so it's a good number. And then these are 2 observations. Actually, it's 1 observation with 2 different gratings for a total of 2,300 seconds. This is like a medium resolution. So that's less than an hour. It's not much, but you can see that the results with less than an hour is already competitive. So these are the 2 sort of observations with the 2 gratings. This is the flux as a function of lambda. Blue and red are the two different gratings. So what happens is that if there is a dark matter signal there, I should see like a bump, sort of like this one. Unfortunately, we didn't discover dark matter. This is helium. It's a very well-known line. But here I show you what we would expect if there was a dark matter signal. So if there was a dark matter signal, this is the red line, is what we would expect. So we have a sort of continuum from astrophysics, and then we have this bump. This is for the case of 1 electron volt. If it was a higher masses, then we would have something here. So
Sorry, the height of the line will also depend on the coupling, I guess.
yes,
No?
exactly. Yeah. So here is for this coupling. The larger the coupling, the larger the signal, the lower, you know, the lower the signal. So that's also important. Just to highlight, the fact that we use the entire wavelength means that we can probe different masses. So each wavelength will correspond to a different mass of the dark matter. Now, I like these slides because I think it's important to have a sort of mindset shift. Because when you typically talk with astrophysicists, no? When now I'm pretending to be an astrophysicist, and I look at a certain target, I know that the galaxy exists, I know it's there, I know the blazar, black hole, they all exist. And when I look with my telescope, I know I'm going to see something, and I want to study better the properties. So when I think of you guys, there is a lot of certainty. You know, it's like this positivity of astrophysicists. When you are a particle physicist, you know that the dark matter problem exists for sure. But you don't know if the signal is there. So when you are a particle physicist, there is really a lot of uncertainty ahead of you. And it's more of a treasure hunt. So where you're sort of looking everywhere, hoping to actually measure a signal. When you don't see a signal, it's also important. I mean, you won't win a Nobel Prize with no detection. But it's important because it kind of narrows down where we are looking. Because right now we have several orders of magnitude of masses that this signal can be. And the more we exclude, the closer we get to actually know where the signal is. So that's a sort of mindset shift that is not always obvious between astrophysicists and particle physicists, but that's the best that we can do right now. So just keep looking different targets, different wavelengths until we actually measure the signal. So now we'll show you the results. So when we don't see a signal, what we typically do is that we write bounds. And what I mean is that we have this parameter space that I'll show you, where we say where the dark matter signal is not. And we already have excluded a lot. So we're already narrowing down. So here I won't comment all of these because it will take me too much time and patience. But the typical parameter space, you have the coupling, so the interaction between axions and photons. You have the mass of the axions on the horizontal axis. All these different curves are different experiments. So you can see there are really a lot of people that are working on this topic. I decided to sort of summarize this in macro category to sort of divide what are the big type of experiments and searches that people are considering. So here, notice there are 38 orders of magnitude in mass that we can have. So that's a lot. In red, we have laboratory searches. So here you have the case in which you have photons that can be converted into axions. That's what happens at CERN, for instance. That's what they're trying to do. I will tell you more later. Then you have astrophysical searches. When you have axions inside, like you have photons inside the neutron stars or the sun, and they can be converted into axions. And that's the green one. Then you have dark matter direct detection. That's the case in which people, for example, at the University of Washington, one famous experiment is ADMX. And you have like a microwave cavity where you use like large magnetic fields. And if the axion is there, it can convert into microwaves. So this is the blue. Then you have the gray. So the gray are the more like an indirect detection, the kind of searches that I do. And I will tell you more about these searches in a while, where you have axion decay, for instance. And that's the band that I was mentioning before for the QCD axion. It lives in this narrow band, but all the rest can still be axion-red particles. Right. So this is not a constraint. Like this is the mass range of interest in my case. So that's what I'm studying with optical and infrared telescopes. So now I will focus to this one. So now we go from like 30 orders of magnitude, 38. We go to this very narrow and clean part of the parameter space. So now we'll show you the few bounds that people work on so that I can compare with what I get. And I prefer to show one by one because I think it's more clear as opposed to put like 5 curves all together and then no one understands anything. Okay, so in the case of CAST, this is the CERN Axion Solar Telescope. As the target is the sun. So you have here the conversion of photons in the sun into axions due to, and then you have like these electromagnetic fields. At the end of the day, you expect X-rays. So that use the Primakov effect. In this case, you can constrain dark matter masses below 2 electron volts. Then you have the stellar cooling. Can ask Jorge everything about it because he's working on it now. Here the target are globular clusters. So as you all know, these are gravitationally bound system of stars among the oldest systems in the Milky Way. And the idea is that we can produce axions in the stellar interiors via the Primakov effect. This axion can freely escape, like neutrinos that escape from the sun. And what happens is that that drain energy. That means higher energy losses. That means more contractions. That means nuclear burning. And if I have a higher rate of nuclear burnings, then I have also this expedites the stellar evolution. So that might affect these evolution phases. No, the main sequence, the giant branch, horizontal branch, and asymptotic giant branch. This can be affected by the existence and the presence of axions. So what people do, there are several papers on this subject over the year. In the most recent, people use 48 globular clusters observed with the Hubble Space Telescope. And they constrain masses a wide range. So that's a powerful technique to constrain a wider range of masses below 10 kilo electron volt. You notice that it's very flat. And the reason is that if you compare the mass of the axions we're talking about, electron volt, with the temperature in the core of these stars, then the axions look like massless from the star perspective. So that's why it's so flat. Then you have MUSE. So MUSE, multi-unit spectroscopic explorer. This is the VLT. This is the wavelength range 1400 to 9350 Armstrong, resolution of 1.25 Armstrong. They look at 5 dwarf galaxies. So in the first paper, they were just looking at LEOT. And then they expanded to Sculptor, Radius 2, Grass 1, Hydra 2. And what they did is that the observation time, again, they didn't ask for time on the telescope. They just look at the archival data. Depending, sometimes there were only 3.5 hours available. Sometimes there were 22 hours. So the observation time really depends. And they constrain their matter masses between 2.7 and 5.3 electron volt. And then there are the VMOS bounds. So this is the visible multi-object spectrograph, also the VLT. Wavelength range 500, 7000 Armstrong, resolution 18 Armstrong. And the total exposure time was 10.8 kiloseconds. The target in this case were 2 galaxy clusters, Hubble 2667 and 2390. And it goes at larger masses, so 4.5, 7.7 electron volt. And now, last one, and then I can show you finally my results. After our paper, like with infrared with JWST, these other infrared constraints have been drawn from the Wine-Red telescope. Warm infrared shell spectrograph for realizing extreme dispersion. This is now at the Magellan telescope. It covers like a lower 0.9 to 1.35 micron. And the exposure time is just, again, an hour for the dwarf galaxies, Leo 5 and 2 nanosecond. So this is between 1.8 and 2.7 electron volt. And now I can see how these constraints compare to what we get. And I will not just show one constraint because we derived several using 2 telescopes. So JWST are actual constraints because I used measurements, observations, where with Euclid, these are projections. 2 sets of targets, because in the case of JWST, I use diffuse emission, while the projection with Euclid are with dwarf galaxies. And I will also show how it changes if you assume an astrophysical background or if you don't. 5 minutes, okay. So in this case, again, coupling as a function of the mass. This is what I get with one observation. So this is just diffuse emission from GI and Z11. And I'm not making an assumption on the astrophysical background. I'm just saying, can I explain the entire of the flux that I observe by saying it's dark matter? Obviously, it's not realistic, right? Because we know that the majority of the emission will be astrophysical. And that's when I assume a continuum model for the astrophysical, from the astrophysical signal. So what I'm looking now, the question now is, can I see a dark matter signal on top of your astrophysical background? And these improve the constraints. They already become competitive with one observations. Now, I open a parenthesis because sometimes people do not want to think of a specific dark matter candidate. Sometimes people prefer to be agnostic and say, okay, but what if it's not axions? Can be one of the many imaginary friends, right? So what the people say, okay, what type of decay lifetime in general, without any particular assumption, did I break something? Maybe. Can we constrain? And you can always translate this coupling into a bound on the decay lifetime. And that means that we can constrain decay lifetime of the order of 10 to the 27 seconds. Now notice that there are not the cast and the stellar Coulomb bound here. It's not that I forgot. Is that those bounds rely on the Primakov effect, and that's typical of axions. So if you don't consider axions, those two just go away because they don't apply in general, while the others do. Now, in that paper, we consider one observation, and it's already pretty cool because we managed to explore a part of the parameter space that was previously completely unexplored. So that's already good. But JWST have observed so many more things. So now in the follow-up, we're considering more targets, over 100. That means more statistics and better targets, so closer to the galactic center. These are preliminary results with NIRSpec. I plan to work also with Mir as well. So in this case, the yellow curve is the one where I'm not making an assumption on the astrophysical background. So it's the equivalent of the black curve. And this is if I consider also the astrophysical background. So I can go down orders of magnitude. I'm constraining up to 10 to the minus 12. And you see that it also covers a broader mass range. The reason is that in that first observation, I was just using 2 gratings, while these 100 targets, they're using more. And that means that I cover more masses. And in terms of decay lifetime, that means that we go above 10 to the 29, which is pretty cool. Now, this was with diffuse emission. And these are actual results with measurements. But at the beginning, I said there are also other targets, in particular dwarf galaxies, that are particularly interesting. So Euclid will be able to observe some of these. So these are 8 classical dwarfs. Euclid will see these 5. These are in the field of view. Drac, Ursa Minor, and Sculptor are the ones that give the best results, typically. While these 3, they're not in the field of view, so who cares? So this is again, it's a preliminary results of what I would expect given the sensitivity of Euclid. And you see that we can go an order of magnitude lower. So we are like at minus 13, which in terms of decay lifetime means 10 to the 31 seconds, which would be pretty amazing. And notice we're not talking about a detector with like great resolution or anything, but you can still do good science for their matter. And now in the last minute, probably, that I've left, I want to tell you a little bit about other ideas that I'm working on. So the preliminary results that I show you were with 1 gigabyte of data. Now we just downloaded 70 gigabytes of data that I still have to play with from both NIRSpec and MIRI. The good thing is that MIRI is looking at other wavelengths. So that means that I will be able to expand way more the masses that I'm exploring. And again, more statistics, better targets. It should improve what I've already done. So that's one natural follow-up. And then one of the reasons I'm here. So I'm working with many people here at the IAC, and in particular, we're looking to the EMIR, the Infrared Multi-Object Spectrograph in La Palma. This covers a wavelength range that is similar to JWST, but we're not looking at diffuse emission. Now we're looking at dwarf galaxies and we're doing something more deep than just 1 hour, for example, of observation. So we hope that by looking at Draco, we might actually observe a signal and then use JWST in order to look at other places as well with diffuse. But then there are many more archival data that are already available. If you look at infrared, you have Spitzer, Keck, Herschel. If you look into optical, you have Hubble, VLT, DESI. Already as data, we'll have more. And I'm working with people in Texas in order to use the IACTalks telescope. In principle, you can have 2 approaches. You can say, I want to study electron volt matter, hence I look into optical and infrared. Or you can have a different approach and say, I'm an expert in X-ray telescope, radio telescope, gamma rays. What type of masses can I constrain? But if you have a spectrograph, you can always use it for dark matter searches. And a lot of time, really, a lot of the data that people, astrophysicists, already have, we can take this data and get results for dark matter. So I think I really advocate for more sort of like projects together between particle physicists and astrophysicists. I think it's fun. We learn more from you guys, and it's always fun to work together. So the summary and conclusion is that in my research, I show that infrared telescope are powerful tools to study dark matter. With JWST, we improve the bounds by up to 2 orders of magnitude. And what's exciting is that there are so many more observations already available, more on their way. So this is just the beginning. And thank all of you for your attention.
So thank you, Elena, for the very nice and pedagogic and didactic talk. Do we have questions or comments?
So thanks for the talk. This is a very naive question, but even if you detect a signal coming from axions, how do you know that they are able to account for the whole amount of dark matter that is needed? Because if I understand it correctly, the signal depends on the unknown properties of the dark matter particle. So, well, suppose that you have axions emitting in the infrared so that you can detect that thing. How do you know that they are able to account for 90-something% of the total gravitational mass of the universe?
That's a good question. So when you look at the here at the parameter space, all what is open still can account for the entirety of dark matter. All is excluded. What you exclude is the entirety of dark matter, but you can still have the 10% of your dark matter come from here. So you can still have that. But here, in principle, you can. Now, in reality, that's a tricky question, but it's a very good one. So in reality, let's say that we observe a signal. Okay, so in principle, first of all, we should be sure that it's a dark matter signal and not dust or other stuff. But okay, let's say that we've done that. We will see the signal in many different targets. If we don't see other signal from dark matter, then we assume it's the entirety of dark matter. Now, in a realistic scenario, probably we have a standard model of dark matter as well. So in a more realistic scenario, we won't find one particle that explains it all. But in a more realistic scenario, we'll have many different dark matter candidates. Now, the reason why people consider, usually make the assumption is the entirety of dark matter, is that we should find one first before looking 10 different. So that's like the assumption that people make. But in a more realistic, probably like we have electrons, we have like many different, we have quarks, probably it will be something similar as well. But yeah. So that's a more realistic. Yeah, we can chat more about that. But this is like the first assumption that you make. Like if you are a Greek scientist 3,000 years ago, you find the electron, you're like excited, you know. But in reality, you know that there is an entire. Now we know that there are more, and probably it will happen the same way. We will find one, and we'll get super excited, and then 3 years later, 5 years later, we'll find another dark matter candidate. And that's probably what will happen. But so far, we still have to find one.
Yeah. So when you're looking for the bump in the infrared signal, if you had a spectrum of similar masses of axions, would you have maybe like a broader, like less discernible bump? And can you confirm or exclude that scenario when you have like multiple masses of similar scale?
Repeat the question because I'm not sure. Let me see what.
Yeah, you mentioned this bump in the infrared signal, right?
Yeah. So you here.
Yeah.
Okay.
Yeah. So yeah, I think you showed another part where you showed like a little bump. Yeah. So if you had like multiple masses with similar couplings and they're sort of like bound together, could they sort of overlap and you have like multiple bumps, like a sort of.
So.
And you have like a.
So in case, let's see that you have like a mass of 1 electron volt, then you have, I don't know, 3 electron volt, you have like 0.5 electron volt. These will be like 2 distinct 3 bumps. Yes. If you have like 2 bumps here, that depends on the resolution of your detector. So it depends how close in mass they are. If you are able to see 2 bumps or 1 bump, depends how far they are. Yeah. So that's where the resolution becomes important. But typically, we don't need like a crazy resolution. Unless, yes, you have 1, 1.1, 1.2. In that case, you will just see a bigger bump. If your detector is not resolving power, it's not great.
Thank you, Elena, for the very nice review. I probably missed something basic here. How does redshift? What is the role played by redshift here? So you're looking here at microns, right?
Yeah.
But then you were talking about the galaxy at redshift 10 or 11, right? So was it equivalent to looking at actions at a wavelength 10 times shorter at redshift 0? Or how does redshift play here?
So yeah, that's a good question. So when I look at the actions in this case, I have to take the signal coming from, when I say along the line of sight, basically it's equivalent to say from all the sort of redshift. You say the cumulative emission. There are ways that you can separate the redshift information. One is the cross correlation technique that I talked to you, to some of you about in the previous, in another talk, where you can really sort of do a tomography in redshift, and in that case you can separate by doing, a tomography with a gravitational tracer. In this case, you cannot. So here, that's why also when you use different techniques, at that point you can also separate that kind of information. But with this, it's hard to do.
But the signal then will not be a peak in a given wavelength. It will be
That's
kind
true.
of
Yeah.
will have some tail.
Yes, yeah, that's also
Yeah.
true. You have some tail, so it will be a different shape, but you can't really say this signal from this technique is coming from redshift 11. You cannot.
So in light of maybe multiple dark matter candidates, would you expect a difference from the signal coming from dwarf galaxies to the one coming from galaxy cluster? In other words,
Yes.
might be a dependence on the environment,
Yes.
the astrophysical context.
Yes, there can be. So one way you can see it is that when you look at the diffractor that I showed before, the diffractor is very different from like diffuse emission. I show it's 10 to the 22, for example, for GNZ11. If you look at dwarf galaxies, typically it's 10 to the 15, 16. So in some environments, it would be easier to see. At that point, though, if you see a signal in one case and you're really sort of confident it's dark matter, at that point you can look elsewhere where you might expect a lower signal with a more powerful detector, more observation time, and you can still observe it. The other thing is like it depends on the model that you consider. So for example, another model that I work on, it's heavier dark matter, and the idea is that these dark matter particles sort of decouple. Okay, they have to. I'm trying to find the easy way, like a quick way to say, but they have to match like CMB constraints, whatever. So what happens is that these populations are repopulated only in certain environments where you have like high velocity. Okay, so in that case, you would expect to see them maybe in galaxy cluster, but not in dwarf galaxies. So that's a specific model. In this case of axions, you would expect everywhere. So that also sort of depends what you're considering.
Okay, maybe we continue with a talk online by Nacho. Nacho, please go ahead.
Hello, can you hear me well?
Yep.
Okay, so my question is related to the modeling of the astrophysical background, because you say that your results change a lot by when you model the astrophysical background. So my question to you is what do you consider astrophysical background when exploring this, and how do you model it?
Okay, so the question is how we model the astrophysical background. So in our case, we model it as a continuum locally. So we basically like a smooth background, and we're asking, can we see a dark matter candidate on top of a smooth background? Now, I just want to stress on one fact: we're not saying that the background is continuum among the entire mass range. It's not one continuum. We're locally saying so among like compared to the line width of dark matter. The background is a continuum. So locally, that's what we do.
In connection to this, if you see a line, how do you convince yourself it is not dust, but it's dark matter?
So if you see a line, well, first you really need to exclude, like for example, here we see a line, right? And we know it's helium. So a lot of time it's a known, very well known astrophysical line. Now let's see that we see a line like here. So one thing is for sure, you talk with a lot of different astrophysicists and you make sure that it's not an astrophysical line, but the other is you look at different targets. The only way is to really, at the end, if I look in one target, I have to find different targets. And a lot of these candidates will also emit in different wavelengths. Like for instance, if you have like heavier particles, you would expect to see both gamma rays, radio, and X-rays. So at that point, you can do a sort of multi-messenger analysis, and that will confirm it's dark matter at the end of the day. But we're still on step 1, finding the secret. So,
Okay, Elena, thank you very much for the very nice talk again, and let's thank her again for the presentation. Just to remind you that she will be with us until Tuesday next week. So if you have any more questions, any more discussions, please go and ask her.